So let me start again. So we were doing this idea that last time about functional random variables. I said a function, a random variable could be x from s to t, and f is a function from t to r, and y is a function of x. So if x is a random variable, y also a general random variable, given that f is a nice function. And we were interested in understanding the distribution of y. Then the second topic was if I had a collection of n random variables, I could take a function f from Tn to R. And I could understand the random variable z, which is a function of x1 through xn. x1 through xn. So now z also is a well identified random variable. And depending on how nice the function f is, then one can also try to understand the distribution of z. So we illustrate this with some examples, how to compute the distribution of y and z. So let me do example 1 was when x was uniform -1, 2, and 0, 2. That means x took values -2, -1, 0, 1, 2 equally likely manner. That is the chance of x assuming any value was 1/5. And if we took the function f of x equal to x squared, then we found out that the range of y was 0 to 1 and 4, 3 values. And then we showed that the probability of y equal to 0 was the same as x equal to 0 with 1/5. If y was 1, then x could have been 1 or -1, and that gave you 2/5. And if y was 4, then x could take the value -2 or 2, and that would give you again 2/5. And that's sort of computed the distribution of y. So both these things, the range of y and the value with which it takes the probabilities, constitute the distribution of y. Similarly, we did this other calculation when I said if z is equal to x plus y, how do I find the distribution of z? So one was I took z equal to 0. That can only happen if x is 0 or y is 0. And the other thing is z could be equal to 1. In this case, what will happen? In this case, x could be 0 or x could be 1, or the other way around. So you could decompose the event as x is 0, x is 1, y is 0, or x is 0, y is 1. And this came out to be 2p times 1 minus p. And similarly, the chance that z was equal to 2 was given by x equal to 1 and y equal to 1. That's the only way it can occur, and that happens with chance p squared. And we use independence of x and y, so x and y were independent to do this thing. So these are two examples we. So what was happening here? I just want to sort of generalize this idea. So in the two pre-examples, what we did was they were known quantities in some sense. They were uniform. We understood it as an experiment, and even x plus y were two random variables. But in general, how would I do this? So in general, if x was a random variable, let's say x random variable that took values on let's say natural numbers and union 0, let's say 0, 1, 2, and so on and so forth. And let's say even y did the same thing. So x and y, y comma x are random variables that took values in 0, 1 up to n. And I had z is equal to x plus y. In general, how would I try to find the distribution of z? So how would I find the distribution of z? So let's try and observe what we did in the previous example, in example 2. So the key idea is the following. So what you do is, first observation is, you see that range of z is also the same as 0, 1, 2, up to 1. So that's an observation you can easily make, because you take two non-negative numbers, you add them up, you'll always land up in the non-negative numbers. So then all you have to do is understand how to compute the probability that z is equal to number n for is what for various values of n. This is what you have to understand. So how does one do this? So one does this by decomposing the event z equal to n. So you take the event z equal to n, right? This is an event. Now how can z be n? Z can be n if x can be, let's say, a number j, and y correspondingly has to be the number n minus j for the sum to be n. Right? Let's go back here. Z is n minus j. And then all you have to do is you have to take this thing and then let me use curly brackets for events. So I have z equal to n is the same as this, and that's just the union of j equal to 0 to n. So that's exactly the way in which z can achieve the value n. When x is j and y is n minus j. And note that n minus j is always non-negative and j is non-negative, so it's well-defined events. And these are the only ways in which z can be equal to n. And of course, now the observation is that they're all disjoint events, because if x is j and y is n minus j, for one j, it can't be anything else. So then you can use the axioms of probability to show that the chance that, let me go back to my green, the chance that z is equal to n, is the same as the probability of this person, but they're all disjoint. So that's the same as, let me write down, that's the same as, they're all disjoint events, so same as summation j equal to 0 to n, the chance that x is equal to j and y is equal to n minus j. If I want to use red, let me use red, sort of erase this j part. So let me go back, j equal to 0 to n, and then x is equal to j and y is equal to n minus j. And in addition, if we were given that x and y were independent, let's go ahead. In addition, if they were given they're independent, let's write that in blue. In addition, if x and y are independent as well, then what would happen? Then you'd come here and you would say, okay, fine. Now that's the same as the sum from j equal to 0 to n, the chance that x is equal to j times the chance that y equal to n minus j. Okay. So this step you can do. So this would be one comprehensive way of understanding the distribution of z. So if you have two random variables that took values in the space 0, 1, 2, all the way up to n, and they were independent, this is one prescription of finding distribution of z. So let me write this down. Let me write this down in a little bit maroon color so it's clear. So this is one prescription of finding. So this is a prescription of finding distribution of sums of independent random variables. That's one idea we have. Okay, this is one thing I have already said. So let's try and see if I can do this for one example. But I want to just spend a couple of seconds on this slide. So this particular step is called is referred to as the convolution of the two functions, of the two mass functions. So let me maybe I'll just illustrate that a little bit more. So in some sense, what is happening is that what we observed here is that what we observed is the following, that your x takes values in the fact x and y belong to 0, 1 up to n. So does z. and then z was equal to x plus y. And then we found out that the probability mass function of z at the point n was the sum from j equal to 0 to n of f sub x of j times f sub y of n minus j, where f sub z was the probability mass function of z, and f sub x was the probability mass function of x, and f sub y was the probability mass function of y. So this you can understand that the if you have if and of course these two are independent was crucial. Independent. So if you have two independent variables and take the sum of them, then the distribution of the new guy is going to be given by the convolution. So this is called the convolution. So of fx and of y. So sums of independent random variables, the probability mass function is just given by the convolution of the two probability mass functions. This is a fact one has shown in the example. Good, very good, very nice. So let me go to the next page. Let me try and do another example. So let me do example. Let's do the example. Let's say example is so example. 3.3.4 in the book. It's a good example. It's an illustrative example of how to do the convolution. But let's just do it step by step. So let me just let's take x to be Poisson with parameter lambda 1. Okay. And let's say y is Poisson with parameter lambda 2. So, and let's say x and y are independent. So now I let z equal to x plus 1. Let's do that first computation. And let's try and find the distribution of z. Let's find the distribution of z. So how would one do this? So again, you do the same thing, like, so x takes values, the range of x, we already know is 0, 1, 2, and so on and so forth. That's Poisson, right? And we also know range of y is 0, 1, and 2, and so on and so forth. And we also know that the probability mass function of x is given by e to the minus lambda 1 to the power k by k factorial, and the probability mass function of y is given by e to the minus lambda 2 to the power k by k factorial. This is for k equal to 0, 1, 2, and so on. So let me just make the whole thing a little bit below. So it's the same thing for both. So this we know, right? So for the previous example, previous calculation, I know that if z is equal to x plus y, so in the previous page I showed this, right? I showed this. If z is x plus y, the distribution of z is given by the convolution of the two probability mass functions. That means I know that f sub z of n is going to be given by the sum from j equal to 0 to n. So let me write the color, and I'm writing a little bit red. Let's see so that I understand what's going on. So let me see j equal to 0 to n. 0 to n. So let's say n is fixed, and that's again in black. And I have f sub x at the point j, f sub y at the point n minus j, right? So let me write that in j, so it's easy to understand. That's what it is. So now I know the expressions for f sub x and f sub y. So what will I get? I just get, this is Let me move to the side so I can sort of start again. Sorry. No. Let's come here. Here is this. Very nice. Come back here. Very good. So this is the same as, so now I have to just plug in for f sub x and f sub j, right? So let me write that down. So let me go summation from j equal to 0 to n. I have that. I have f sub x at j, right? So let me j equal to 0 to n. F sub x at j. So what will that be? E to the minus lambda 1 to the power j over j factorial. Right? I'll have that. And here I'll have, again, let me write that in a little black so it's a little bit distinguishable. So e to the minus lambda 2 over n minus j factorial, and then I have lambda 2 to the power j. That is what I have, n minus j. So let me write this also in black. So all the terms that don't depend on j will be in black. So I have e to the minus lambda 1 to the power j. So this is again, this in red, so it's clear. So I have lambda 2 to the power n minus j, n minus j, and then n minus j factorial. This is what I have. Right? This is the exact thing I have. But now you can observe that what all terms don't depend on j. So let's see, so e to the minus lambda 1 will come out, lambda 2 will come out, and I have the other part. So I have e to the minus lambda 1 plus lambda 2 at the top, that will come out. And then I have the sum from j equal to 0 to n, so j equal to 0 to n, I'll have that. Then what's inside, what's left is lambda 1 to the power j, so we have that in j, and then I have lambda 2 to the power n minus j, right? So I'll leave that as it is. So I won't take that out. So I'll leave that as n minus j. And then I have divided by, I have j factorial, right? And then I have a n minus j factorial. This is what I have. So now we are all in familiar territory now. This looks like a sum of two things. We can understand the expansion a little bit. So what I do a little trick. I just write this as e to the minus lambda 1 plus lambda 2, that's at the top. I leave it like this. I multiply and divide by an n factorial. So an n factorial outside the sum. Then I take this sum that I have here, right? Sorry, I'm just making a mess of this. Very nice. I have to copy this. I bring it here. Then I have multiplied an n factorial there. So I multiplied by an n factorial inside as well. So nothing much changes. But then this person here is just like the binomial expansion. So e to the minus lambda 1 plus lambda 2 outside. The whole thing divided by n factorial. And if you just stare at this a little bit, this is just the fact of lambda 1 plus lambda 2 to the power n. That's just a fact using binomial expansion. This is binomial expansion. In this step, that's all I've used. Right? So that's a very nice, crucial way of understanding it. But now we're here, right? So that means the chance of z equal to n is given by lambda 1 plus lambda 2 to the power n by n factorial. So this is true for any n, in let's say 0, 1, 2, up to so on so forth. I have fz of n equal to lambda 1 plus lambda 2 power n into e to the power minus lambda 1 plus lambda 2 divided by n factorial. So what does this mean? This just means that z is distributed as Poisson of lambda 1 plus lambda 2. So we have shown an interesting fact that if x and y are independent random variables, each of them is Poisson lambda 1, lambda 2. The sum of Poisson is again Poisson. Right? So one can also generalize the calculation. One can generalize quite easily. This is an exercise one can, I'll leave it as an exercise, that if x1, xi are all Poisson lambda I, I equal to 1 up to k, and I had z is the summation I equal to 1 to k is the xi, then it just adds up. Then the distribution of z is just going to be Poisson of the sum from I equal to 1 to k of lambda. Of course, I need xi, the crucial fact, I need this Poisson, z is equal to this, and I also have to take xi as an independent. So this collection is independent. So if I have a collection of independent random variables, they add up to Poisson. So let's just recap what we did so far. Let me see if I can get that split view for you. Very nice. Go here. Go here again. Again, split view. Very nice. So let me make this a little smaller. We go to the previous page. Go to the next previous page here. And then here is this page right here. Right? Make this a little bit smaller and we can recap a little bit. Oh no, not big, or smaller, or smaller. So the idea was the following: if I had independent random variables x and y, I sum them, I call the new random variable z, then the probability mass function became the convolution of the two individual mass functions, and that we implemented in this example of Poisson. So we took two Poisson, lambda 1 and lambda 2, both independent. You took z equal to x plus y, and then I found out that the random variable z had the following distributions. You could do z equal to x plus y here, and then what you would get is that z was Poisson lambda 1 plus lambda. And one can generalize this. If you have k random variables, all Poisson, and they're mutually independent, then the following fact also is true. This is one simple calculation of doing this idea. Now, suppose I do a calculation like I want to do before. Let me go back to my whole screen. Very good. Next page. Very nice. Now I ask you a different question. Let's say I ask you a different question. I say again, I'm in the same example. Let's say I'm going to part B. Let me go back to my blue. Part B of the same example. And I ask you the following question. So x is Poisson lambda 1. Y is Poisson lambda 2. X and Y are independent. X and Y are independent. And I have Z is equal to X plus Y. This I know how to compute the distribution of Z from part A, right? So from part A implies that Z is Poisson of lambda 1 plus lambda 2. Now this, I want to ask you a question from an experiment. Let's say I'm given the event Z is equal to N. So I'm going to ask you, what can X be? So X given Z equal to N, what's the distribution of Z? So let's say N is equal to 0. I give you this Z equal. What is the distribution of Z? X. So what's the conditional distribution of X given Z? So this is a little tricky one. Let's see how to do this. We know how to do Z equal to N. We know how to do X. Let's see that. So now, one thing to observe is the following. So the first observation is the following. So how do I find it out? The first observation is that if Z is equal to N, then Z is sum of X plus Y. Y is non-negative. Then X can only take the values. X has to belong to 0, 1, up to N. X can't take values more than that. Right? Because This is because z is equal to x plus y, and y is also already in 0, 1 up there. Okay, that's what it is. Let's get back to this. This is where we are. So now, how do I do this now? Let's see. So now, suppose I want to calculate the chance that I'm given an n is fixed, right? N is fixed, n is fixed. So then the chance that x is equal to k given z is equal to n, this is where I'm at. So let me go back to my old notation of making k as red, so you can understand what k looks like. So the k is in the set, so k is in 0, 1 up to n. So now this, how is going to be, this is going to be equal to, so how do you do this, is the chance that z is equal to n at the bottom, by definition. At the top, you'll have x equal to k and z equal to n. This is what you, by definition of conditional form. But now you know that that's the same as x equal to k, and here you'll have what is z? Z is x plus y. X plus y is n. The whole thing divided by the chances z equal to n. Right? So now, how does one finish the problem off? So the bottom we know how to do because it's just Poisson lambda 1 plus lambda 2. The top, how do you do? You look at this way. So z is equal to n. The top you do a little trick. So you know x is k. So you know x is k. So that's easy to do. So your x is k. That's k. Then what you do is you interpret the event x plus y equal to n, because x is k now, so I can replace the value of x by k above, so I get y is equal to n minus k, right? Y is equal to n minus k. Right. Let me just do this in black so it's clear. So y is n minus k. That means all I'm doing is that inside this event, right, this whole thing event, all I've used the fact is that if x equal to k and y is equal to x plus y is equal to n, that's the same event as x equal to k and y equal to n minus k. You have two same events. That's what I've used here. Right? So now I'm in business now. Now I know how to do this now because now I can use the independence of x and y. So I have x equal to k, probability y equal to n minus k, and the whole thing divided by probability z equal to k, y equal to n minus k. So let me do one small thing. Let me erase this and write it in green. So I'll use observations in green. So in this step, what have I done? I've used the fact that the event x equal to k and y equal to n, sorry, x plus y equal to n is the same as is the same event as x equal to k and y equal to n minus k. Right? And here here I've used the fact the independent. Very nice. So once I have these two facts, I have the following idea that I know the answers now. So this guy is going to be equal to e to the minus lambda 1 to the power k, so I like doing k, whole thing divided by k factorial, that's at the top. The next term is e to the minus lambda 2 to the power n minus k, the whole thing divided by n minus k factorial. And then you know, the whole thing divided by z equal to n, which you know is Poisson lambda 1 plus lambda 2. So e to the minus lambda 1 plus lambda 2, lambda 1 plus lambda 2 to the power n by n factorial. So I do this whole jugglery, I do up and down. So I'll get what n factorial at the top by k factorial, n minus k factorial. And then I have all the e's will cancel off. So and only lambdas will remain. So I'll get lambda 1. So maybe I'll read next line. So this is too short to write it here. So maybe I'll move it across. So let's see this whole thing. So this whole thing will move across. So is equal to this, and this is equal to, like I said, n factorial by n minus. So let me write this in red, by k factorial, and then I have an n minus k factorial, and then I have, what do I have? I have lambda 1 by lambda 1 plus lambda 2 to the power k, and I'll have lambda 1, lambda 2 by lambda 1 plus lambda 2 to the power n minus k. So where did I start? I start off with this distribution. X is Poisson, lambda 1, y is Poisson, lambda 2. They're both independent. I looked at the fact, I want to understand the fact that x given the fact z is equal to n. I want to understand its distribution, and I came up with this formula that probability x equal to k given z equal to n after this computation gave me this answer, that it's this way. But this, if you stare a little bit, what do you get? This is the same as, how do you stare it? So now, so what have we shown? So we have shown, we have shown the chance that, so therefore, the chance that x is equal to k given z is equal to n, sorry, given z equal to n is in black, sorry about that. Oh my goodness. Given z is equal to n is the same as n choose k in my notation, and this I'll write a little differently. I'll write it as lambda 1 by lambda 1 plus lambda 2 to the power k, and the inside the other part I'll write it as 1 minus lambda 1 by lambda 1 plus lambda 2. So let me erase that again properly. Lambda 1 plus lambda 2, the whole to the power n minus k. So what happens here? So if you, and this is all valid for k in 0, 1 up to n. So what's the punchline here? Let's stare at it a little bit. If I have x is Poisson lambda 1, y is Poisson lambda 2, z is x plus y, then x given z is this. So what have we shown? We have shown a very interesting fact that x given z equal to n is just binomial with lambda 1 by lambda 1 plus lambda 2 as the p, and it's other way around, right? Np. So binomial n comma lambda 1 by lambda 1. So let me just do a split view and show you what the whole calculation is, so you can enjoy the calculation a little bit. So the previous page, let me go here. Let me go back to the small one. Small version of it. This is what we have shown. It's a nice idea, right? So you have two Poisson independent, you condition on the sum, then the individual become a binomial. It's an interesting idea. Intuitively, you can think about it. There's sort of an explanation for Poisson. We did it by an approximation of, it came as an approximation to the binomial, but there's sort of an interesting idea of Poisson in terms of a queuing model. Then this interpretation will become even more clear. But as of now, we will leave it like this. Let's come back to it. The calculation. So let me just close off with a theorem, and then I'll. These ideas are widely applicable everywhere. Let me go back to the normal view. Next page. Let me go back to this whole thing. I know what's happened. Why is it not coming the whole time? So let me close off with a theorem, this class. So the idea is that So this theorem is called theorem 3.3.5 in the book. And the idea is that let x1, x2, xn be random variables. On a, let's say, for the time being, I think this is the simplest way to do it on a single sample space S. Sample space S. Let f be a function from be a function of n variables. Variables on such that z equal to f of x1 up to xn is well defined on S. So then the probability, so the key thing we used in all the examples was we try to understand the probability that f of x1 to xn is in an event B on the real line. That was the same as the chance that x1 to xn was an event f inverse of B. That's exactly what we use in this whole example. This for any B, which is subset, any B in event in the range of any event B in the region. I'll let you prove it yourself, but I'll just give you a sketch of the proof. I'll give you a sketch. The key idea is that, which we are using the examples as well, is the following idea that a sketch of the main part. The key idea we used was that the event, the set of all S in S, such that f at the point x1 of S, f xn of S, xn of S is in the event B. This, if you use the definition of a function, this event is the same as the set of S in S such that x1 of S, xn of S is in the event F inverse of B. So this is a set theoretic inequality. So once you understand this, then the theorem is immediate. So once the set theoretic notion, set theory fact. So once you understand this, then the result is immediate. And this is what we've kind of used in the examples.